Thank you so much for the
Yes.
invitation. It's a great pleasure to be here, and it's a great pleasure to see everyone meet with the new people. So today I'm going to talk about a topic where some of you might have heard before. I wanted to keep things on the application level because of the name of the seminar, Dynamic Games and Applications. So I'm going to talk about how we can find the optimal policies in large population games, specifically with the applications to epidemic control. So this is a joint work with Alexander Ora, René Carmona, and Mathieu Laurier. At some point, we were all in Princeton, but now we are all scattered all around the world. So the motivation for this papers and the follow-up papers started, of course, during the Corona time when I was doing my PhD. So what happened is that in March, when I was in the US, at the beginning of March here, you can see that the Corona started and the possible lockdown policies are started to be discussed. So in just like 12 days, we realized that actually the lockdowns are going to start. So in 12 days, from the possibility of discussing whether the lockdowns should be, we came to the point that the lockdowns are going to be implemented. Then what happened is that we started to discuss whether these lockdown policies were late, whether it would have been better if they were implemented earlier. For example, later in the year, in May 2020, it was shown that like if the lockdown was started earlier, actually many more lives could have been saved. Later on, after some time, for example, 2022, slowly these mandates, for example, lockdowns and the mask mandates slowly started to disappear. But what happened is that people didn't follow these policies exactly. Even if there was no mask wearing policy, some people wore the masks. On the other hand, even if there was a policy to wear a mask, some people didn't obey these rules. Another thing is that, for example, during these holiday times, even if there was a surgence of the virus, some people didn't care about this after some time, and they, for example, travel freely. So in order to take into account this type of behavior of the individuals who are not following the policies exactly, we wanted to look at the models where we can incorporate game theory. So before going into the details of our model, I wanted to talk about what type of different approaches can be used in epidemic modeling. So what happens in the classical epidemics models, in the math biology especially, is that people look at more compartmentalized models where you look at the system dynamics from a higher level. In this case, we look at the system states as susceptible people, infected people, recovered people, exposed people. For example, the exposed people are the people who are exposed to this illness, but they are not showing any of the symptoms. So there are also some micro versus macro viewpoints. The basically system dynamics level models are generally shown with the ODs, where the proportions of these possible health condition states are modeled with ordinary differential equations. However, if you wanted to look at more like individual focused models, you can also check the agent-based models, where you can look at basically computational models. However, in the agent-based models, the good thing is that you can have many heterogeneities. You can try many different, the effect of the policies, but there is no tractability. You can't end up with a closed form solution, or you can't talk about optimal policy. The thing you can do is that you can look at the effect of the policies and you can try how it works out in different scenarios. So basically what we wanted to do after seeing these models is that what is going to happen if the agents are strategic? And how can we decide on the optimal policies if we take into account this strategic behavior of the people? And the other thing that we are going to discuss later on is that what is going to happen if the players are not identical? Because what happens in the corona is that some people were getting very significantly affected, but some people were not even showing the symptoms. So even if we start from the most basic models where we assume that the people are homogeneous, it is ideal to go to the case where we are going to put heterogeneities in the model models for the people. So in this talk, what's going to happen is that for the first question part, we are going to incorporate ideas from game theory, specifically mean field games and the Stackelberg equilibrium between a principal and the mean field population. Then we are going to go for the second part, modeling the heterogeneities through graphon games. By the way, if you have any questions, you can always stop me or like send it on chat. Like I'm happy to stop and explain things. So for the outline of this talk, what's going to happen is that I'm going to start from the case where the principal is going to give some specific policies. So when this principle, where you can think of as the government, is going to specify the policies, I'm going to introduce the agent population's behavior. Agent population is basically going to be the people in the society who are deciding on their socialization level. In the first part, we are going to go to the direction of finding the optimal policies for these large number of agents in the society. And in order to do this, we are going to introduce the principles model. And we are going to see that when we have the principal and the mean field population, it is going to be a bi-level problem. And in order to solve this bi-level problem, we are going to propose a numerical approach. So in this part, I'm going to give this a specific numerical approach we propose in the related paper, but later on in the follow-up work that we don't exactly focus on epidemiology, we extended this approach to cover more general mathematical model forms. And I'm going to give a small side note about that. And after this part, the second part is going to be only like the last 10 minutes possibly. And this part is going to be the graphon games part where I'm going to add the heterogeneities to the people, because in the first part, we are going to look at a mean field population where the people are assumed to be identical and symmetrically interacting. On the other hand, in the graphon case, you can look at totally heterogeneous people on the continuum, and you can look at an underlying network structure among them. So therefore, in this case, we are going to need to characterize the equilibrium with a continuum of ordinary differential equations, and we are going to propose a numerical approach for these ones. And we are also going to discuss the existence of the solution in this part. So let's start with the first one, where we try to find the optimal incentives in a Stackelberg mean field game, specifically with the epidemics application. And do you have any questions for now? Okay. So our motivation in general for the Stackelberg mean field game is basically we want to find an optimal policy for a large population of people who are optimizing their own objectives. And in this case, we are looking at an epidemic mitigation problem. So we are directly going to focus on that problem. In this type of problems, what's going to happen is that between the government, let's say, and the people in the society, we need to look for a Stackelberg equilibrium. So what is Stackelberg equilibrium? Many people here are basically experts on this, so I'm sure like they can explain much better than me. But for the people who are not very familiar with the term, let me introduce what it is. So in the Stackelberg game, in the classic form of it, we have only two players. The first one is the leader, where I call principal in this talk most of the time. And the second one is the follower, where I call agent. So the leader normally chooses some incentives, or you can think of these as policies, and the follower is going to give the best response to these incentives. At the end, the leader is going to optimize these policies or incentives by taking into account the best response reaction of the follower. So this equilibrium type is totally different than Nash equilibrium, because in Nash equilibrium, both players give their best responses given the other person's behavior, and then we need to solve a fixed point problem. However, in this one, leader is doing an optimization given the follower's reaction as a function of the leader's behavior. The thing is, normally what's going to happen is that in our application, instead of having only one agent, we have a big agent population, a large population. And in this type of large populations, it is generally very hard to find some kind of an equilibrium. These people in the population are going to basically choose their socialization levels, and they are going to show some effort to slow the spread of the illness, and they are not going to be cooperating. This means this doesn't mean that they are being selfish. It means that they have their own objective function and they are optimizing their own objective function. So then the principal is going to take into account the Nash equilibrium response in the full population instead of taking the best response of one agent as in the classical Stackelberg games. So therefore, our aim is to find a Nash equilibrium here, which is going to be a function of the principal's policy, then plugging it in the principal's objective function and finding an optimal solution for the principal. So in this point, we are coming to the question of how can we find a Nash equilibrium in large populations? Again, we have many experts here, but for the general audience, what we can do is that we can approximate this game among the large number of agents by using some kind of mean field approximation. Since we have non-cooperative game, basically we are going to be looking at a mean field game. So mean field game is basically going to assume that the agents are identical and they are infinitesimal. It is a little bit counterintuitive, but what's going to happen is that it's going to take the number of the players go to infinity, and in this way, the specific person we look at is going to become infinitesimal. And since the agents are identical, and since they interact symmetrically, which means that each agent is interacting with every other agent at the same level in the same way, we can focus on a representative agent. And this representative agent's interaction with the population distribution. This distribution, of course, can be the distribution of the states in the population, or distribution of the controls in the population, or the joint distribution of the states and the control. And actually in our model, it's going to be the joint one. So then what's going to happen is that the Stackelberg mean field game model can be written, which means that the principal is going to set some incentives. Given these incentives in the agent population, we are going to find the mean field game equilibrium, which is going to approximate the Nash equilibrium. And we are going to plug this into the principal's problem to do the optimization of the principal. So here we need to discuss, since it is an epidemics application, how the model for the individual people in the mean field game can be constructed. So the idea comes from the compartmental SIR model. So this model is introduced in 1927, very old, but it is still very widely used, and it is its extensions are widely used in the math biology community. In this model, we have a system level look. We have the proportion of susceptible people that we show with S, proportion of infected people that we show with I, and the proportion of infected people that we show with R. From S to I, from S to R, I, the proportion is going to decay depending on a meeting rate beta, and the proportion of infected people in the system. If we have more meetings and if we have more people infected, the transitions from S to I is going to be faster. And from I to R, generally we have a constant recovery rate that is shown with gamma. Then this model can be modeled with ordinary differential equations that you see here. But the problem is that this is a system level problem and it is not an individual level problem, and we want to focus on the individual's behavior. So in order to do this thing, we are going to go to the individualistic case where we are going to consider n many agents. And we are going to focus on agent I. Agent I can have health status states that can be susceptible. They are not sick, but they can be sick. They can be infected or recovered. This recovered sometimes is also removed, which includes that too, or you can add more like health status if you want to. We assume that the pairwise meetings between two agents are going to happen at random with rate beta. And then we can show the basically the state jump of this specific agent with a continuous time Markov chain where the transition rate can be seen here. So this says that from S to I, this person is going to jump after an exponentially distributed time that with the rate beta and the proportion of infected people. So this idea directly comes from SIR. And from I to R, the person is going to jump after an exponentially distributed time with rate gamma. But here is that we basically modeled the individualistic behavior, but we didn't model the control of the people. We need to introduce some kind of control in the model. So in order to do this thing, we need to realize that the probability of infection has decreased by the actions of the two agents that are meeting in a multiplicative way. This means that when both people are restricting our behavior further, this effect should be shown in a multiplicative way. So to show this, basically, we are introducing a control for the agents that is called contact factor. You can think of it as a socialization level. It is between 0 and 1, continuous. If it is 1, it is the regular normal level of socialization or contact level. But if it is less, basically the people are being more cautious and they are restricting their behavior more. So for example, if it is 0.5, you can think of it like people are wearing masks when they are interacting, something like that. In that case, we can basically change this continuous time Markov chain as follows. This is, as you may remember, is for agent I. So this jump from susceptible to infected for the agent I is going to depend on this agent I's own socialization, but also it is going to depend on every infected person's average socialization level. So this means that if every other infected people are staying at home, they are going to have this alpha tk equals to 0, then this multiplication is going to be 0. So this person I, even if they are socializing at the same level as before, they are not going to jump from S to I because every infected people are in their home. In the same way, even if all the infected people are socializing at some level, if this agent I is staying at home and choosing alpha ti equals to 0 for all the times, there is no jump between S to I. So in order to have this intuitive understanding, there should be a multiplicative interaction between the controls of the agents. So this was the finite player case. We are, of course, going to go to the infinite player case to look at the mean field game. So this is the part we are going to look for the equilibrium behavior in the population. So at this point, for now, let's assume that the principal is setting some incentives, and for now, they are exogenous. Later on, we are going to discuss basically its finding in the talk. So let's say that the principal is setting incentives lambda, which is going to be time dependent, and psi, which is going to be F terminal T adapted. So it is going to be depending on the full state process of the individuals in the agent population. For the application, you can think of this part as the social distancing or mask wearing, those type of non-pharmaceutical intervention level. So if it is 1, there is no intervention. If the lambda is lower, it is going to be further intervention at that specific time. And psi, in the paper, what we were saying is that it's like a stimulus check that is going to be paid at the end of the time period. And this stimulus check is going to be basically paid depending on whether these people were sick in the meantime, whether they were susceptible all the time, etc. So then, given these incentives, let's look at the agent population. For the agent population, we are going to assume that we have a large population and actually we are going to take the number of players goes to infinity. And then we can basically approximate the game with an extended finite state mean field game. It is extended because we are looking at we are looking at the interactions through the joint distribution of the state and the control. And it is finite state because our states are the health status, like susceptible, infected, recovered. So in this case, the cost for the representative player can be written in a general form as follows. They are going to be choosing the control alpha, and they are going to be interacting with the full population through the joint distribution that we show with rho. When I use bold symbols, it is the full-time process. So then the objective of the representative player is to minimize the cost that you can see here. We have a running cost that depends on the time, the state of the agent, whether this person is susceptible, infected, recovered, whether this person is the level of the socialization level of the person, and the population status through the joint distribution of the year state and control. The principal's incentive, the time-dependent one, is going to affect the running cost, and its F-terminal T-adapted one is going to affect the terminal utility of the agent. As you remember, our application assumes that this psi is a stimulus check, and we get a utility from it. So since this is a cost function, we have a negative sign here. In this case, basically, we have our cost function. We want to optimize this over alpha, which is our control, which is the socialization or the contact rate. And then we have the state, or health status is going to change depending on our control and our interactions with the population. So here, this part gives us the expected contact rate or expected socialization level of the infected people in the society. So when the infected people socialize more, we are going to jump, the representative person is going to jump from S to I in a faster level. And if this person decides to socialize more, they are going to jump from S to I faster. So this is the full model for the extended finite state mean field game in the general form. Later on, I'm going to give more specific examples, but for the transitions, it is directly from the epidemiology idea. Then our question is, how can we define the equilibrium in this model? We introduced the problem basically, but we need to introduce the definition for the equilibrium. Equilibrium here is defined as follows. There should be two conditions. The first one is that the control should be the best response for the representative player given the population's distribution. So we keep the population constant. We find the best response for the agent. So this first condition is basically saying this. Alpha hat is going to minimize the cost of the representative player given the joint distribution in the population. But then the second part is the regular fixed point condition that we observe in the Nash equilibrium definition, which means that this joint distribution should be the joint distribution of the best response control and the state induced by it for the representative player. And this is because the players are taken as identical. So all of them should behave in the same way. So in this way, we are going to say that this control and the joint distribution couple is the mean field Nash equilibrium given the incentives lambda and psi. Then here I'm going to mention these equations later on, but for now I'm just giving the idea. A forward-backward stochastic differential equation system is going to characterize the mean field Nash equilibrium given the incentives. Of course, there are other ways to solve the mean field games too, but we went through the probabilistic approach. And this probabilistic approach, we are going to end up with the forward-backward stochastic differential equations. The challenges of these equations are that they are coupled, and these are Makin-Vlasov type of equations, which means that the distribution of the process is in the dynamics of the process. So these are specifically hard to tackle. So after discussing the mean field problem, we can introduce the principle to complete the full Stackelberg mean field game definition. So in the principal part, basically, they are going to have their own cost. In the cost, this cost form can be, of course, different than the individual agent's cost form. They are going to have a running cost part where it is going to depend on their own policies and also the proportion of the health status in the society. This P is the proportion of the susceptible, infected, and recovered in the agent population. So you can think of it as the principal is going to, for example, is going to have a high cost if the proportion of infected in the population is high at that time point. We can also have the terminal cost. In the terminal cost part, since this psi is taught as a stimulus check, it is going to be coming as a cost, and we can have a terminal cost that is going to depend on the proportion of the health status in the population. So here we have an expectation because this psi is going to be a function of the full X process of the agent population. So it is something random, even if lambda is just a function of time. So then the principles optimization problem is not just optimizing this thing, because if it takes the P as exogenous, it is not enough. It would be Nash equilibrium. It should take this P as the Nash equilibrium response of the agents. So the principle is going to try to optimize this thing by taking into account the reaction, the Nash equilibrium reaction of the agents. So this P, as you see here, is going to be taken as a function of the principles on incentives lambda and psi. There are some other conditions too. This is a little bit coming from the contact theory models. So in the contact theory models, it is very common that the principal and the agents have a conflicting interest. So basically, the principal may be better off if the cost of the agents is higher and higher. To prevent the cost of the agent goes very high, we are also going to put a condition of the cost of the agents, the representative agent in the society should be smaller than a reservation threshold that is shown with kappa. Any questions?
One question. Is the midfield equilibrium unique for given policies of the principle?
Yeah, so it depends, of course, to the model. So in the paper, we gave the conditions that it is going to be unique. Of course, you need a lot of convexity, and like for the existence, you need a lot of Lipschitzness, and for the uniqueness, you need a lot of convexity-related assumptions or the monotonicity-related assumptions. But in general, how this thing is treated in the Stackelberg mean-field game or the principal many agent models is that we say that principal, even if it is not unique, principal can choose the Nash equilibrium in the society and can take the one that it wants. But in this paper, we assume that there is uniqueness.
Okay. Okay. Clear. Thanks.
Yeah, of course. And some other nice discussions related to that, if there are multiple Nash equilibria, for example, if the principal is choosing, then we can do regret analysis, and you have like papers related to that already. They can look for the worst case situation, best case situation, etc. But I haven't looked for those type of things. Yeah, maybe, hopefully in the future.
Yeah.
Okay. So then we are going to discuss how we can solve this optimization problem. So these type of problems are pretty hard to tackle analytically. So in this part, we are going to discuss a little bit numerical approach by rewriting our problem. So for this rewriting, I'm going to discuss this epidemic specific model, but later on, I'm going to discuss a more general model form application, because in this one you're going to see that we have a very specific condition that we need to satisfy. So here I put the model. We have the principal's objective, This is basically what government wants to minimize. This is the proportion of susceptible, infected, and recovered in the society. So the principal is interacting with the people in the society through these proportions. And they also have some costs related to their own incentives, lambda, which can be taught as the time-dependent non-pharmaceutical intervention level, and the psi, which is the random F-terminal T adapted stimulus check. So this is their objective, but this objective is constrained by the Nash equilibrium. This P hat here is going to be actually the distribution of the X, where X was the health status of the people. Previously, I said that the mean field game, Nash equilibrium, can be characterized by forward-backward stochastic differential equations, and we can see them here. We are using the characterization of the value function. So here the forward one is going to be the state dynamics at the equilibrium. And the backward one is basically characterizing the value function. So the terminal condition for the backward equation, since it is characterizing the value function, is going to be the terminal cost of the representative agent in the mean field game. And if you remember, they were getting some utility from the stimulus check. So this thing is going to be the minus utility function from the psi, which is the stimulus check. So then what we are going to do is that we are first going to realize that these forward-backward equations are basically coupled. So one option can be to solve the forward one by keeping the backward constant and then updating the backward one with the solved forward, then updating the forward one with the backward, and basically doing this type of backward and forward updates. However, this is going to be very, very inefficient. So the first thing we do is that in order to solve these equations that are coupled at the same time discretization, we are changing the backward STE for this value function to a forward STE. So as you see, we have this from T to terminal T. We are going to change, and we are going to just change the signs here, and we are going to have from 0 to T. But now we need to choose the initial position for this y0. This is an unknown. This is going to be chosen by us, and our aim is basically ending up at this terminal condition that we need to end up. However, we have a very good condition here that the terminal condition of this agent is related to the terminal cost of the principal. So we are going to assume that this U function is invertible, and we are going to take this terminal condition and plug that in the principal's problem. So yt is equal to minus u psi, and psi is going to be equivalent to u inverse minus yt. So we are going to plug this information here, and then we are going to say that now we have a new stochastic optimal control problem where the controls are the initial position for this y0, the social distancing policy over time, which is lambda, and we are also going to control the coefficient in front of the randomness, where this part is the jump process. So here, we don't have the psi control, which is a stimulus check control anymore, because it is going to be determined by this term here, and that part is going to be determined by all these y0, z, and lambda choices. So then our task is basically solving this new stochastic optimal control problem. In order to do this thing, it is going to be our very helpful friend, artificial intelligence, which is using neural networks. So we went to the neural network side for this problem, first because of nonlinearity. We wanted to end up with more realistic features in the models. Second, we can increase the dimension of the states as much as we want, because the thing that is going to change is only the node numbers in some layers. So we are going to introduce neural networks to approximate the controls, which are lambda y0, initial position for this backward equation, and the z. So lambda was a time-dependent incentive. So it is going to be a function of time, and it is going to be given for each type of health status. For the representative player, they are going to be lambda S, lambda I, and lambda R, which means that if you're susceptible, you need to have this policy. If you are infected, you need to have this policy, so. For Y0, it is the value function at time 0. So it needs to be a function of the state, where E is the state space, and it is a scalar. And for the Z, it is actually related to the derivative of the value function. So it is going to be a function of time and the state space, and it is going to be the state dimension, R on the state dimension, which is M. So our final goal is basically discretizing the time and minimizing this cost that we want to minimize here. Of course, for these dynamics, we are going to discretize them too. We are going to start from an initial x0. Y0 is going to come as the output of the neural network, and we are going to basically compute the Monte Carlo simulation for the x and y. However, what happens is that this is a mean field problem. We need to find the distribution of the x, where x was the health status, SIR. So in order to find that thing, we need to basically simulate, Monte Carlo simulate a population of size, let's say n. And then we are going to use the empirical distribution that we get from this Monte Carlo simulation, and we are going to use stochastic gradient descent to basically find the best parameters of the neural network. So for this model, as I mentioned previously, we needed to have this condition of the terminal cost of the representative agent in the society, and also the principal to be related to each other. However, this is a very restrictive assumption. So in order to get rid of it, we worked on another paper. If you're interested in, its name is a machine learning method for Stackelberg mean field games. So here, my short tour is related to that. We look at, in that paper, a generalized Stackelberg mean field games. And for this type of things, actually in that paper, we are looking at the continuous state version. Of course, the finite state version is going to follow similarly. But the idea is that we can end up with a similar model. Now we have more general terminal cost for both the representative agent and also for the principal. But when we have this different terminal cost, we are not going to be able to have this trick of putting the terminal condition directly to the principal's problem. So what we do is that we do the same thing of changing the backward equation forward in time and starting from an initial y0. But we realize that we need to end up in the terminal condition that is going to be definitely set. So this is going to be equal to the terminal cost of the agent. This is now general G. Previously, it was utility from psi. And for the principal, we have a general terminal cost G0. Previously, it was just psi. And what we are going to do is that we are going to say that we change this backward to forward, but we add a constraint, which means that the terminal condition needs to be satisfied. But then, how are we going to solve this constraint problem? We are going to relax it with a penalty, and we are going to write it as a basically penalized stochastic optimal control problem. So here we basically propose a similar numerical approach, but the important part of the paper is that we show that the solution of this penalized stochastic optimal control problem converges to the solution of the original general Stackelberg mean field game problem, of course, when the coefficient of the penalty nu goes to infinity. So in that paper, we do this theoretical analysis. But a very important side remark is that we don't discuss the existence of the Stackelberg mean field game solution in this form, which is a very hard open problem that is very interesting. And if you have any ideas, I would really like to talk about them. So let's go back to the epidemics application after this short detour. Let's look at one example. So in this example, for the running cost of the agents, what we have is that the principal sets some policies, lambda s, lambda I, and lambda r. Of course, they are time dependent. And our agent wants to be close to these levels. As you see, they are choosing lambdas to minimize the distance between the lambda s and alpha, which is their control, lambda I and alpha, lambda r and alpha. For the infected people, we also have the treatment cost because not everyone has a very good healthcare, and in the United States, healthcare is very, very expensive. On the other hand, for the principal, what's going to happen is that they want to flatten the curve. This was a term that we heard a lot, but let me remind you, it means that they want to minimize the proportion of infected at each time step. And then the other thing they want to do is that they want to set policies, lambda s, lambda I, and lambda r, that are close to the recommended policy. So here there is Center for Disease Control and Prevention, CDC, and throughout the pandemic, they were recommending a specific lockdown and mask policies. And we are assuming that our government is a cooperative and they want to be close to these recommended policies. Of course, it doesn't have to be exactly the same because they are going to find the optimal according to their taste. So when we look at the results, the first result we check is actually just looking at the mean field game solution given the principal's policy. In this one, we are not doing the optimization of the principal's policy. What we do is that how the people respond if on day 40, the policies that we show with the dashed lines are suddenly more restrictive. Please remember, when we have this lambdas lower, it means that they are more restrictive. So the blue ones are for the susceptible people, and the orange-red ones are for the infected people. So what we see is that on the top plots, we have the explicit solution. This problem can be solved with the finite scheme if you look for the HJB and KFP equations also. And at the bottom, we have the solution of the numerical approach. And we are able to see that our numerical approach is good at mimicking the explicit solutions. Then after this sanity check, we are going forward to the general Stackelberg mean field game problem part, where we are going to do the optimization for the policies of the principles too. Here on the left, we have the, again, semi-explicit solutions for this problem. On the right, we have our numerical numerical solutions results. And again, our numerical solution is good at capturing this behavior. These two examples were for more, like the sanity check. What we wanted to do later on is looking at more extended problem, and we are looking at more health status. For example, we have the exposed people here, and we are adding the deceased people. The transition rates are here shown. We have the mean field interactions, again, this time from susceptible to exposed people. So what we observed in this one is that the dashed blue one is the optimal social distancing policy set by the principal. The blue solid one is the corresponding mean field Nash equilibrium behavior for the susceptible people. And the red and the orange ones are the policy and the corresponding Nash equilibrium behavior of the infected people. So what we see is that for the infected people, we have a more restrictive policy. For example, government says them, okay, you need to quarantine, and the infected people follow this rule, which is good. But for the susceptible people, for what we see is that for this model parameters, the principal, the government, is setting just a little bit restrictions. Maybe it says that in the crowded places, you need to, if you have like more than 20 people, you need to wear a mask. But what we see is that the people are further making their behavior more restrictive. So you see the blue solid line is more restrictive than the dashed line, which is more restrictive than the optimum policy. This is at first pretty surprising for the non-cooperative people, because what we would assume is that if you don't need to follow the policies, you would always try to be more relaxed. But when the health is the concern, this is not true. What happens is that when the people care about their own health, they are being more careful. So this is, I always give this example. When I was in PhD, on campus, we didn't need to wear a mask. Only in the closed places we needed to wear a mask. But all of us were still wearing a mask, and sometimes people were warning each other outside, saying like, why don't you wear a mask? So this type of behavior is shown in this type of game theoretical models. So in the last 5 to 7 minutes, I guess I'm just going to mention a little bit how we can put heterogeneities. This part is going to be pretty quick because it's building the previous model. We are going to look at something called graphon game. So what's going to happen is that, again, the agents are going to choose their contact factor. They are not going to be cooperating. They are going to be optimizing their own objectives, and they are going to be heterogeneous. This means that they are going to have non-symmetric interactions. This can be, for example, like you may interact with your neighbors more, you can interact with your age group more. Further, they are going to have individual rates for infection, recovery, etc. For example, older people may have a worse recovery rate. So then the population is going to play a graphon game. So what is a graphon game? In the graphon game now, since there is no homogeneity, we are going to look at a continuum of labels, agents, and they are going to be labeled with X. This X is going to be on continuum between 0 and 1. And these agents are going to see a weighted aggregate of the agent behavior. Previously, if you remember, the agent was interacting with the population through the expected control of the infected people. But now this control of the infected people, as you see here, is going to be weighted by a function that we call graphon. So graphons are going to take two things, let's say I and J. This I and J are going to be indices of two people, and it is going to give us the interaction level between two people. In general, graphons are designed to be symmetric. Of course, there are non-symmetric extensions to that too, but we are going to assume that they are symmetric and they take values between 0 and 1. Then our aggregate, which was the expected contact factor of the infected people, is going to be changed to introduce this weights between the specific agent X and every other agent. So now we are not going to be looking at a representative player. We are going to be looking at agent X, and agent X is going to have their own aggregate that is shown with ZTX. And then previously we had this transition rate matrix. In the current case, what's going to happen is that we are going to have a agent-specific beta, agent-specific contact factor control, and this part is going to be the new aggregate, as you see here. So we are adding further heterogeneities. And finally, the costs are going to be individual costs also. You can have different cost coefficients, different cost forms. So then what we give as the theoretical result to this is that we can write a coupled Kolmogorov-Fokker-Planck and Hamilton-Jacobi-Bellman forward-backward system of continuum of ordinary differential equations to characterize the graphon game equilibrium. So here it is continuum because this is, as you see, indexed by the agent index X, and this X is on the continuum between 0 and 1. So that's why we are seeing here the equation system only for one person, but this equation system is actually on the continuum. We have the forward part, which is the KFP equation that gives the state distribution. We have the backward one, which is the Hamilton-Jacobi-Bellman equation that characterize the value function. As you see, we have the terminal condition for that. And for the state distribution, the KFP equation, we have the initial condition. So then what we give as the theoretical result is that we show the existence of this continuum of ODEs. In order to do this thing, I'm very briefly going to say is that we are going to use first Banach fixed point theorem to show the existence and uniqueness of this aggregate given U and P processes. And then, but given the existence and uniqueness for this Z for given U and P, we show for U and P by using the Schauder that there is an existing solution. So the final part is basically mentioning a little bit the numerical method. Here, I'm going to briefly just say that what we do is that the same idea. We are going to replace this backward equation with the forward version. And we are going to choose the initial condition for this backward equation. We are going to implement a neural network to choose it. And then we are going to try to match the terminal condition. If you remember, this was our terminal condition, which says that the value function should be equal to the terminal cost of the agent. So then our idea is basically minimizing the error between where we ended up with the neural network initial condition at the terminal time and where we should end up. Of course, since we can't do this for the continuum, what we are going to do is that we are going to do mini batch. So I was saying that like the same idea is going to apply. We are going to change the backwards equation, which is the HJB, and we are going to write it as a forward one. And then we are going to choose the initial condition to match this terminal condition. So then what we are going to do is that we are going to end up with a terminal part where we choose the initial position with the neural network, and we are going to try to minimize the error between where we end up and where we should end up, which is the terminal condition, which is the terminal cost of the agent. But this is on the continuum. Of course, we can't do this for the continuum of particles. So what we do is the mini-batch stochastic gradient descent, and we are going to sample S many agents, and we are going to n many agents that are in the set S, and we are going to do it for them. So I was showing this last example here. It was for the power law graphon. Power law graphon is here. So what happens is that for an agent X, if the index X is higher, it means that they are connected to the other people with a higher strength. This means that basically when this basically says that there is some kind of a super spreader effect. So the people with the higher index are more connected, so they are going to be infecting other people more. So what's going to happen is that in these plots, if the person has a higher index, they are darker color. So we see that the aggregate for the higher index is indeed higher because they are connected to the people more, which means that they are at higher risk to get infected. Therefore, they are decreasing their control further, as you see in this darker black one. But this is still not helping them to offset this negative effect of the high aggregate. So at the end, they are having a higher probability of being exposed, higher probability of being infected. So to conclude, basically what we did is that we discussed both Stackelberg mean field games and the graphon games in the epidemic mitigation application. What we basically did is that we look at Stackelberg mean field games to find the optimal policies for a government. Then we looked at the graphon games to include heterogeneities because our motivation was to see in Corona different groups were getting affected differently. So after this, basically, I'm going to thank you. And I'm very sorry for the technical difficulties on my part here.